students. My name is Chaitanya, Physics faculty at Shakthi International School. Today, in this video, we are going to learn an important topic from chapter AC, that is alternating current, from class 12th. Alternating current. Okay. The topic that we are going to see is circuits of alternating current consisting resistor, capacitor and inductor. That means if in an AC circuit, if we are having a resistor, okay, what will happen to the EMF? What will happen to the current? We have to analyze. We know AC current, that means alternating current. Alternating current. The EMF is E naught sine omega t. Or else I can write the voltage produced due to it is V naught sine omega t, since it is always going to be changing, function of time. In the same way, we have to find what will happen to the value of current I when the circuit is consisting of resistor, capacitor and inductor. Okay. So then now let us analyze with a resistor first. Okay. Resistor, capacitor and inductor. Let's say this is your resistance which is connected to an alternating source. Here a capacitor is connected to an alternating source and inductor is connected to an alternating source. Okay. Now the EMF that is going to produce V is equal to V naught sine omega t. Here also the same, V is equal to V naught sine omega t. The V you are going to produce here, okay, is also going to be the same, V naught sine omega t. But here you can observe the voltmeter can be connected to it. The voltmeter readings of resistance, capacitance and inductance we can understand. Okay, and the current passing through that equation we have to write. In this setup, okay, we know according to Ohm's law, V is equal to I into R. From this condition, from this circuit, we can write I is equal to V by R. That means I is equal to V place, we can substitute V naught sine omega t divided by R. So this expression can be further written as I is equal to I naught sine omega t. Now if you observe, these are the two equations. This is called phase. Omega t is the phase. Let's say this is phi 1, this is phi 2. If you are trying to understand what is the phase difference, it is 0 in this condition. So there is no phase difference between the current and the EMF which is passing through the circuit of a purely resistive circuit. Okay, this is for a purely resistive circuit. In a purely resistive circuit, we understood what will be the equation of V and I. Okay, now we have to understand about purely capacitive circuit. You know the general formula of capacitance, C is equal to Q by V. Can you write the voltage across the capacitor is equal to Q by C? Yes. Now we know that the entire voltage in this entire circuit should be equal to 0. If you are applying KVL, Kirchhoff's voltage law, okay, we can write V minus VC is equal to 0 in this entire circuit. Okay, that means V minus Q by C can be equated to 0. If you are writing this equation further as V is equal to Q by C, you can write the equation of Q is equal to V into C. So from this equation, Q can be written as V naught sine omega t into C. Now, to understand the current in this circuit, I, which is nothing but dq by dt, I can differentiate this equation d by dt of V naught C sine omega t. If sine is getting differentiated, we are going to get cos. So this can be written as V naught C into omega cos omega t is the equation of your I. So you can write this entire expression as, if I want to express it in the form of I is equal to I naught sine omega t form. I want you to bring it in this equation. I want us to bring it in this analysis so that we can compare it to V is equal to V naught sine omega t. Now if you are trying to bring it into this condition, what will happen to the equation of current, we will see. I naught, now from this expression you can write I is equal to V naught by 1 by C omega. Okay, where 1 by C omega will represent you the resistance that will be provided by this circuit. Okay, XC we can write. This is called capacitive reactance 1 by C omega. This is actually acting as the resistance due to capacitor. This is what? Capacitive capacitive reactance. Okay, now if you are writing it in that form, you can write the equation of this one in the form of I is equal to, okay, I naught, where I naught is equal to, okay, I naught is equal to V naught by 1 by C omega, okay, into cos omega t. Still it is not in the form of sine, so I wanted to write us to write in the form of sine. Can I write this one as omega t plus pi by 2? Yes. Okay. I can write the equation of I is equal to I naught cos omega t as I naught sine omega t plus pi by 2. Since sine is positive in the next second quadrant, omega t plus pi by 2, if you are changing it, it will become cos omega t again, which is not making a big difference for us. So now if you are analyzing it with V is equal to V naught sine omega t, this is phase phi 1, this is phase phi 2. If you are analyzing the phase difference delta phi, you can write that omega t plus pi by 2 minus omega t will give you the change in phase, the phase difference as pi by 2. Okay, I hope you are understanding. In this, the current is leading or the voltage is leading. If you observe, the current is leading. Okay, that means if let's say this is your V, okay, the current equation is leading by pi by 2. This is your I. Okay, this is your current I. This is for purely capacitive circuit. Okay, current will be leading by pi by 2. Now if we are analyzing the same, if we are trying to understand for resistance, this is the direction of resistance voltage due to resistance, this is voltage due to capacitance, and the current due to resistance is also in the same direction. But if you observe, the magnitude of that IR is comparatively less, because IR is nothing but VR divided by R. I naught of R is nothing but V naught of R divided by R. That is the reason why magnitude of I will be smaller. The same goes here as well. You can draw your VC a little big. Okay, but VC will be lagging behind, current will be leading ahead by pi by 2, lagging behind by pi by 2. Now if we are trying to understand the inductor, okay, so in inductor condition, the voltage in the inductor EMF E is can be written as minus of L into di by dt. This is the general formula for induced EMF, and obviously it will be in the opposite direction. So if you are writing again Kirchhoff's law, you can write in this entire expression, okay, V minus L into di by dt should be equal to 0. So that means V is equal to L into di by dt. From this expression, I can write V by L is equal to d by dt. So di can be written as v by L into dt. So what is v? V is nothing but v naught sine omega t into dt divided by L. Now, if you want the total current I, you can integrate on both sides. So integral of di is equal to integral of v naught sine omega t into dt divided by L. Now, if we are further integrating this one, okay, so I will be coming out as v naught by L is constant into integral of sine omega t dt. Now, if you are integrating this function, sine will become minus cos. So minus of v naught divided by L into cos omega t divided by omega we have to write. So the final function of it we are getting it as v naught by omega L into cos omega t. This is the value of current I. Further, to bring it into that general form, we can write I is equal to minus of V naught divided by XL now, where XL is the inductive reactance. Inductive reactance. Okay, into cos omega t. Further, you can write the same as I is equal to I naught cos omega t. Negative sign is there yet. Okay, so where I naught is nothing but V naught divided by XL. Further, if you are writing this cos omega t, we have to analyze with respect to sine, right? So minus of I naught into sine of omega t pi by 2 minus omega t. I can write this as the expression. Sine pi by 2 minus omega t is nothing but cos omega t. Further, if you are multiplying this inside, you can write, sorry, wait a second. We can write this one as omega t minus pi by 2. Okay? Omega t minus pi by 2. Okay? When the equation of this negative sign is multiplied inside. So you can write, okay, I is equal to, okay, I hope you understood that. Initially we are writing it as 90 minus pi by 2, that is pi by 90 minus omega t, which will give you cos omega t. Since already a negative sign is already outside, we are writing sine of minus sine theta as minus sine of minus theta. So doing that, we will get I naught sine pi by 2 will be becoming negative, omega will be becoming positive. So this is the final expression of current. I is equal to I naught sine omega t minus pi by 2. In this equation, in this inductance condition, your V is equal to V naught sine omega t. From this condition, you can observe the voltage due to, if let's say this is your V due to capacitance, current is lagging behind. Current is lagging behind. This is here. And how much angle it is lagging behind? At a by an angle of pi by 2. Because the phase difference that you observe from here will be omega t minus of omega t minus pi by 2. So these two gets cancelled. You will be getting pi by 2 as your phase difference. Okay. So when we are having these kind of resistors, capacitors and inductors, the final output, okay, you can understand for a purely capacitive circuit, for a purely resistive, for a purely capacitive and a purely inductive circuit will be given as, if I is equal to I naught sine omega t, if V is equal to V naught sine omega t, I will be equal to I naught sine omega t, where I naught is equal to V naught divided by R. In purely capacitive circuit, if V is equal to V naught sine omega t, current in this equation can be written as I naught sine omega t plus pi by 2, where I naught can be written as V naught by XC, and XC is nothing but 1 by C omega. Okay. Now, in purely inductive, if V is equal to V naught sine omega t, I can be written as I naught sine omega t minus pi by 2. So your I naught can be written as V naught divided by XL, where XL is equal to L omega. Okay. I hope you understood this well. We'll meet in the next video. Thank you.